Hello everyone. In this video we are going to talk about one-dimensional elements in finite element analysis. There are many problems in engineering, as you know, that we can handle with 1D elements, with line elements. And if you look at my ANSYS videos, there are several of them that I have used line elements. So they could be heat transfer in like a fin, fluid flow in like a pipe, vibration in trusses, frames, bucklings of columns, and so on. So these are where 1D elements or line elements can be very useful. So let's look at this 1D elements a little bit with more details, although we have seen them in trusses and in frames and beams in my previous videos. But let's take a look at them, and this time as the example, we are going to look at heat transfer problems, the type of problems that we have not so far looked at. So here, the type of elements that we have seen in the past are basically the line elements, right? The linear elements, where you had two nodes on the two ends of the element, and the parameter, whatever it is, whether it's displacement, temperature, or anything, we assume that it is changing linearly over the element. So if the element is from xi to xj, and the temperatures, let's say, on the two ends of it are Ti and Tj, then the temperature either linearly increases or decreases from one node to the other. So you only have two nodes per element. And so you can, as I said, write that physical quantity as a linear function. Now we learned we can write it as the dot product between two vectors. One is the nodal values and the other one we call the shape functions. And in the case of a linear element, these shape functions are also linear functions of the location, as you can see here. And we have seen this Si and Sj in my previous video on columns. So here, let's say here is a fin. On one side it is attached to a base with a base temperature. On the other side it is exposed to the fluid with fluid temperature. And let's say T of base is bigger than T of fluid, so the temperature in reality would drop like this, like an exponential function kind of. And you can approximate this by a bunch of linear functions that are continuous. Okay, and each function is written like this: SITI plus SJTJ. One thing I have to mention before I move forward is the length of these elements do not have to be the same. So although they are all linear elements and everything, but we don't have to make these elements all the same size. Typically, where we have a lot of variations, like here in the beginning of the fin on the left side, we have a lot of changes. There we can have shorter elements, so they can capture a lot of the variations. Okay, if we use basically larger elements, longer elements, then the approximation is going to be very bad. So it's good that we use a bunch of shorter elements at the beginning, and then once it kind of flattens out and goes to a plateau, then we can use what? We can use larger elements. So the size of these elements do not have to be the same in general, and keep that in mind. And that's what we did in our ANSYS videos. You see I added a refinement, right? In the areas that I see big changes, like for example in the stress concentration areas around the hole, you see that I use the smaller elements. So this is what you really need to keep in mind. Okay. Now, we learned about shape functions also in the previous video, that we can write them in the local frame instead of global frame. So instead of capital X, we can use a small x, which starts at each node. The first on the left node, in this case, in general, on one of the nodes of the element, and it only goes from 0 to the length of the element. So we can write them in terms of the local coordinates. The other thing we learned is that each one of these shape functions is 1 at its own node and 0 at the other node. So we learned that, for example, if this is x and this is s in general, for this linear case, if this is 1 and this is 0 and this is x of I and this is x of j, we learned that one of these shape functions goes like this, and the other one goes like this basically. So this blue one is Si and the red one is Sj. Each one is 1 at its own node and 0 at the other node. And also, if you take derivative of these two functions and add the derivatives together, you see some of the derivatives is 0 at any point, and you can see why. The derivative of this guy is negative 1 over L with respect to x. The derivative of this guy is 1 over L. When you add them at any point, sum of the derivatives is equal to 0. So these are some extra properties of these shape functions that I wanted you to know before I move forward. Now, in a quadratic element, so still the shape is 1D, still a line, but we add more nodes. Why do we add more nodes? So that the temperature variation, let's say in this case, within the elements is not necessarily a line. It could be like what? Like a parabola. And you can see if I use elements of higher order, like a quadratic here, instead of a linear one at location 1, I can capture this curvature a lot better than a straight line. So in general, when we have higher orders, because of the flexibility we have, and we can shape the change the shape of the element, then we can get better accuracy. So in this case, we have 3 nodes on the same element. There is 1 here at the beginning, 1 at the end, and 1 in the middle, and we can call them ij, and the one in the middle k. And here we have 3 nodal values, t, I, j, k, using which we form a vector, and we have 3 shape functions, si, sj, and sk. Of course, definitely these functions are going to be quadratic. As you can see, there are 2 x's in them multiplied together. And again, if you look at each one of these nodes at their own, each one of these shape functions at their own node, they are 1, and everywhere else they are what? They are basically, in this case, if we plug in, we'll see that, let's see if they are 1 or not. So if I plug in x of I here, right, would I get 1? Well, xi minus xj is the total length, so it's going to be L. Xi minus xk is half of the length, which is L over 2, multiplied by 2 and divided by L squared, as you can see here. And the answer is, of course, what? 1. But if I plug in xj here or xk here, one of these two terms will be 0 as well. So you see that same property that each one of these shape functions is 1 at its own node and 0 at the other nodes still applies here. Now we can go to higher orders, and this time we have a cubic element where we have 4 nodes on each element, and they are at the beginning L over 3, 2L over 3, and the end of the node, and we can call them I, K, M, and J. So we have K and M in the middle added. And so we have 4 nodal values and 4 shape functions, and again, the shape functions here are absolutely third order or cubic. And again, the same property applies. Si is 1 only at x of I, and it is what? It is 0 at the other nodes, okay? And one way that you can find these coefficients is by basically plugging some numbers in. So remember, let's say I want to find Si, okay? I don't know the form of Si. So should I memorize it? The answer is no. So how do I find Si here? Well, I say Si should be 0 at x of j, x of k, and x of m. So definitely it should have these 3 terms. Okay, this is what we call the Lagrangian interpolation. So the form of it is some constant a times x minus xj, x minus xk, and x minus xm. That's how the form of this Si should be. The question is, what is this a? Well, all I need to plug in is xi here and see what I will get. I should get a 1. Well, how much is it? Xi minus xj is clearly what? As you can see, it's negative L, right? xi minus xk is negative L over 3, and xi minus xm is negative 2L over 3. So this A times those three entities should be equal to 1. So clearly A is the reciprocal of the product of them. There are three negatives, so I need another negative to make it all positive 1. And the product of all this is what? L cubed 2 over 9, right? So it's 1 over that, which is 9 over 2L cubed. And that's exactly this guy here. Right? So finding these coefficients is not that hard. As far as we are concerned, basically each mode shape is the product of x minus the x of the other nodes times some constants, and that constant we can find it by saying that that mode shape is 1 at its own node. Okay, so you don't need to memorize any of this. If you forgot, you can always find them. Okay, and cubic node, of course, you have 4 control points, and you can get to capture more dynamics here. So this gives you more accuracy, of course, at the price of more computations, but you can do it. So these are 3 of the elements that you might see in software like ANSYS. And you might always go with higher elements, higher order elements, but there is a trade-off between accuracy and the computation time. So I showed you that, for example, most of the time ANSYS goes with the quadratic element, and it gives you the option to drop the middle node and make it a linear element like this. Okay, so you have the option to change the order. Now, with that in mind, let's go ahead and try to basically use the linear elements and capture the heat transfer problem formulation in finite element analysis. So if I have an object like this fin, on one side, as I said, is attached to the base with some temperature, and on the other side exposed to the fluid, let's say air or anything, with fluid temperature which is less than the base temperature. And the conductance in this material is K. The cross section of it is A. The perimeter is P. And the heat transfer coefficient of the fluid is H, or you might call it the film coefficient, right? In ANSYS, H. So these are the parameters that you have in this case. The governing differential equation in this case is what? Ka d squared t over dx squared equals minus hpt plus hptf equals 0. And I don't want to derive it in this case for you, but basically this is coming from the conservation of energy, okay? So if you look at each element, there is some heat coming in and there is some heat going out, right? So what you can do is consider a small element here, like this, with some small length dx, and look at the heat that is coming into it through the conduction, which is negative Ka dt over dx, right? And then the heat that is dissipated through the top, the bottom side, right? And the left side and the right side, and then there is a heat that goes out of the right face, correct? So this is your element. And as I said, there is some heat coming in through conductance, some heat going out through the conductance, and then it is dissipating heat to the fluid through what? Through these 4 red arrows. Let me use a different color so you see the difference here. So the greens are the conductions and the reds are the convections. And some of these should balance out, right? Therefore, you can find their relation, the differential equation like this, and again you can derive it yourself. My goal here is not to teach you heat transfer, but that's the governing differential equation. As you can see, it's a second order, it is linear, and there is this non-homogeneous term which you can take to the other side. So second order with constant coefficients, linear, and non-homogeneous with a constant term, okay? Which, of course, there is exact solution for it as well, which you learned in heat transfer. And again, as long as there is exact solution, I would not do finite element, but sometimes the geometry of these fins and the problem is so complex that we cannot find analytic solutions. There you can resort to FEA. So what are the boundary conditions for this governing ODE? Well, at the left side at T of 0, if say this is x of 0, T of 0 equals T of base. On the right side at this area here, then you have what? You have basically different scenarios that you can have. What are the different scenarios? Well, if the fin is very, very long, then you can say that the temperature has been reduced so much along the fin that at the tip, the temperature of the tip is the same as temperature of the fluid. Okay, this is a very simplistic assumption, and it's only valid when the fin is literally infinitely long or very, very long. Okay, so it's a theoretical assumption. It's not valid really most of the times. Sometimes you might insulate the tip of the fin, or you neglect the heat loss through the tip. Again, either you have to do insulations on the tip, or again, it has to be very long. So you can neglect the heat loss and say that basically this conduction term at L is equal to 0. Most of the time, the fin is not that long and it's not insulated, it's just exposed to air. So you have to account for the heat loss through the last element. Therefore, you use this equality, which is the heat coming from the left end of the last element is equal to the heat lost from basically the tip. Okay, and so these are possible different scenarios for end condition here, for the right end. Now, how do we get our matrices? In this case, the conduction matrix, which is equivalent to a stiffness matrix for solid mechanics problems, and then the load matrix, the thermal load in this case. Right? If we find them, then we can find the temperature distribution and the nodal temperatures in this case. So our final solution should be something like K times T equals F, where F are the nodal thermal loads, K is the conductance matrix, and T are the nodal temperatures. So if we can find these two, then we are good. And the method of choice typically for heat transfer problems is the residual method, and it's the Gallerykin method. So I briefly explain it. It has a lot of derivations, which you can find in the textbook that I mentioned to you in my channel. It's the finite element analysis, theory and application with ANSYS by Dr. Saeed Moaveni. That's one of the very best textbooks on theory of finite element. I recommend you get this book and look at it, okay? It's a very good book to have. And in that textbook, the derivation all the way to the very end and manipulating the second terms into first terms and using chain rules and everything is shown. My goal here is not to go through all of that math, but I'll tell you the essence of it. So here, let's say I have two elements, adjacent elements, E and E plus 1, and they have three nodes, I, J, and K. As I said, they are linear elements. And here, we do the residual method. If you remember, the residual method was what? Well, we assume a solution for this T. We assume some solution, right? And we plug it into the differential equation. Because it's not the exact solution, the right-hand side will never be equal to 0. So we call that non-zero term, we call it a residual term, which is equivalent to this, where T of assumption is plugged in here and here. And then we integrate that residual term multiplied by what? by the terms, by the functions phi, where phi's are the members of that assumed solution, right? And we multiply them by those and integrate them over the whole domain and set it equal to what? 0. Just watch one of my previous videos which called formulation methods in FEA, right? So that's the essence of the Gallerykin's method. So here we do the same thing. Basically, at this moment, I'm focused at this node J, the middle, the intersection node. So if I want to find that integral and set it equal to 0, how should I do that? Let's take a look. So I plug in the assumed t into my differential equation, and whatever it gives me, which is not 0, I call it the residual term. Good. I multiply it by what? By the phi, the weighting function, which in this case is Sj, integrated from the whole domain over the whole domain and set it equal to 0, right? So this is your phi. And of course, since this is node J, use Sj, and remember Si and Sj are what? Basically the components of the assumed solution. This T is your assumed solution, right? And these are your phi's, right? Or phi 1 and phi 2, you might call them. So here, what I do is I multiply this residual terms by phi j for node j. If it's node I multiply it by Si or phi I and set it equal to 0. Now, the thing is, for this node j, not only this node j will get one term from this left element, which is this guy, it will get another term from the right element because it belongs to both of them, and that is this one. Here, as you can see, I have a different residual term and I have a different weighting function, which are integrated over the new domain. Add them together, and then this total addition is equal to 0. Why? Again, because this belongs to both of them, so the total weighted residual should be equal to 0. And if you can see why these phi's and r's are different, because one of them is coming from what? From element E. The other one is coming from element what? E plus 1. Since the assumed solutions are different for these elements, right? The temperatures, the nodal temperatures are different, so S's are different, and the assumed T is different, so everything is different. So this total thing is going to be what? 0. But of course, for node I, if I want to write it, Ri, well, here, if it's just the beginning element of my whole object and there is nothing on its left, then I only need what? I only need to integrate this from xi to xj, because it's only this one element on the left, and this is going to be si of which node, of which element? Element E, and then the residual term belonging to element E, the integral of that dx should be what? Equal to 0, and the residual is, of course, k a second derivative of t with respect to x, and then minus hpt, and then plus hp tf, right? So you see, for the first node and the last node, the residual term is just 1. For any node in between is 2. So if you do that for all of these nodes and then set all of these total weighted residuals to 0, that gives you what? That gives you sufficient number of equations along with applying the boundary conditions, that from which you can find the elemental conductance matrices and the thermal load matrices. Okay, and when you go from this area to this final results that I'm about to show you, there is a lot of mathematical derivations. Okay, you have to apply some basically chain rule here to the second term and convert it into first terms, And then it gives you a couple of terms here, right? One that comes to boundary conditions, one directly to the conductance terms. So there is a lot of derivation here involved, and for the sake of time, I skip them and I just show you the final result. But again, you can refer to the textbook. So if you want the conductance matrix now for all of the elements except for the last one on the right, the conductance matrix for all of them is going to be from two terms. One is from the conduction between the elements, and the other one is from the heat dissipation through perimeter of that element and through convection. Now remember, we call this conductance, but it doesn't mean it's just the conductance alone. It is basically whatever heat that is going throughout this element. So it is related to all of the faces, not only the left and the right elements, the faces of the element, as I said, from the preference as well. So don't be tricked by saying because this is conductance, then there should be only K term in it. No, it calculates all of the heat coming and going through the element. Okay, so there is an H term and there is a K term. Okay, because you are writing your differential equation into a simple form like this. And not only this term will contribute to the something times T, this term here also contributes to something times T. Okay, that's why you see something here. Now, for the last element, if the heat loss for the last element must be accounted for, as I said, that's the most realistic condition that you can have, which is this guy. That's the most realistic condition. And if that's the case, then the conductance element matrix, for the last element is going to be similar to this top one plus an extra term. You see, they are the same except for one extra term. If it's neglected, then you neglect this last term, okay? If there is no heat transfer through the last element. But if you have to account for it, then you have to add this extra matrix to those two extra terms. What about the thermal loads? Again, for all elements except for the last one, it is going to be HPL over 2, 1, and 1. For the last element, again, if you have to account for the heat transfer, you have to add something extra to it, which is this guy. If that is negligible, then you get rid of that. Okay, so these four formulas, you have to use them. But again, this one and this one are for all of the elements, except for what? The last one, this one, and this one are only what? For the last one. So when you write this equation, okay, you have to be careful that for the last one, right, what you put into the K and what you put into the F, they are going to be a little bit what? Different, especially if the heat loss here is not negligible. Okay, so just be careful about the last row of K and the last element in F, which are related to TF. You have to pay attention to them. Okay, now let's look at an example together. So here I have a composite wall, and it's made of 3 layers, and these layers have their own Ks and they have their own thicknesses. One side is 200 Celsius and the other side is fluid at a constant of surface of 200. The other side is exposed to convection with H of 40 and T of fluid of 30 Celsius. And here we're going to use 3 elements, each element for one of these walls. Why do we use one element in each wall? Because everything along the wall is constant. So this is like the simplest thing you can do. Of course, when it says the temperature distribution along the wall, So here what we want is to go from this number to this, to this, to this using 3 lines. So you would get something like this, for example, right? You get 3 pieces of line. If you want to capture the real dynamics of everything, you better use more elements per wall, per portion of the wall, okay? Or at least use higher order elements. But here we go with simplest FEA analysis possible. The minimal number of elements, 3, and the simplest type of element, line. Okay, linear elements. So that is like the simplest thing you can possibly do, just to reduce the computations, the manual computations. So, for all of the elements, except for the last one, we learned that F or K is Ka over L, 1, negative 1, negative 1, 1. HP over L6, 2, 1, 1, 2. So that's exactly what we are going to do here, right? And here, the thing I have is, for the first wall, there is nothing on the perimeter. The only area that there is fluid is what? Is on the right side of wall number 3. There is no fluid here or on the left or right side of it, so there is no H term around the perimeter of this, right? So if I draw this wall in 3D, like this, then there is no fluid here, there is nothing here, there is nothing here, and nothing on the back side. So that H term here is going to go to 0 because I don't have fluid on the perimeter of it. The only term I have is conductance, Ka over L, and that's what you see over here. The K is plugged in, 0.08, A is plugged in, right, which is 1 here. We assume 1 to make the problem simple. So we assume that the A for all of these objects is 1 unit, and L here is 0.05 or 5 centimeters, right, here. And so in terms of watts per degree Celsius, this is going to be the K for matrix 1. What about the thermal load? Well, thermal load, if you look at it, the thermal load comes from H. You have it when you have convection around the perimeter, and again there is nothing here, so F for this element is all 0. Similar thing happens to element 2. Again, element 2, above it, below it, left and right, there is nothing. So very similarly for element 2, that H term is 0, so the load is 0, and K2 is again Ka over L, 1, negative 1, negative 1, 1. Okay, so this is very simple problem. There is nothing above or below the walls. Now for element 3, nothing on the perimeter, so again for element 3 this term is 0. Okay, but you have to account for the heat through it, so this term you cannot neglect because there is some convection on the right side of it. This is for convection on the right, this is for convection on the perimeter. There is nothing on the perimeter, but there is something on the right, so this term you have to account for, and that's what you can see here. And again, if you go to the load, this term, which is the perimeter, is going to go to 0, but this term is not. So that's what you can see over here. Right? So this is K of member 3, and this is F of member 3. Now you combine matrices 1, 2, and 3 together, which are these 3 matrices, right? And you get this global K for the whole wall, and of course those are going to be something like this. This is one of them, K1, this is going to be K2, and then K3 is going to be like this. And of course, in this overlap areas, one of them is here and one of them is here, the entries are added together. And similarly, F's, right? The F's are like, one of them is like this, the other one is like this, and the other one is like this. Okay, so there are again overlap areas, but these overlap areas are all in zeros. So you add them together, and now you say K times T equals F. Now, do I have any boundary condition? Yes. What is it? It's T of 1. T at node 1 is 200. So you add that condition here, that 1 times T1 equals 200. And so now the only unknowns you have are these 3 T's. You solve for them from the equations of row 2 all the way to row 4. And these are those temperatures that you can see, 162, 39, and 31. So as I said, the temperature per location is going to be what? It's going to start at 200, then drop to 162, then a big drop to 39, then a small drop to 31. So you get something like this. Okay? And this is at 5, this is at 20, and then 30 in centimeters. This is in degrees Celsius. Okay, of course, it's 3 pieces of lines. Again, you can use more elements, you can use higher order elements, and do a lot better analysis. So hopefully this video was useful to you and you learned a little bit more about 1D elements and how to perform heat transfer analysis for 1D problems. I will see you in my next lecture. Thank you.